Okay, so in this video, I am going to show you how to make a simple current source using hopefully components you have in a typical electronics shop, namely BJTs, bipolar junction transistors, and Zener diodes, and a couple of resistors. So there's two different types of current sources. Well, there's sinks and sources, and today I'm just going to talk about this source. So it's using a P-type transistor. So here it is. So this is variation on what would be a more simple type of transistor current source you may have seen, where this component here is just a resistor, but in this case we're going to use a Zener diode to keep the voltage at the base of this transistor a little bit more constant, and to basically track the voltage at the rail a little bit better so that it's more stable. Okay, so a quick recap of Zener diode IV curve, which we talked about IV curves of diodes in the previous video. But the Zener is different than your typical diode because its characteristics do look typical, or at least similar to what we saw in for the just regular silicon diode. It has this this is volts versus current IV curve. So it has a typical on voltage, but in the reverse bias case, as you can see here, this is more like an exponential. So this thing doesn't actually become constant, but in the reverse bias case, the voltage across the diode, so the voltage across the diode is constant in the reverse bias case at the Zener voltage. And this is the guy we're using today. This is the IN4337 A, and its turn on voltage is just a little bit more than its Zener voltage is, like, I think 5.3 volts. So that's what we're going to use to this constant voltage drop across the diode is what we're going to use to stabilize the voltage at the base of the transistor and keep a constant current flowing. So what we need to do is be somewhere along this curve to get the constant voltage. So we do need to set we also need to set IZ. We need to set the current through the Zener diode such that it's in full saturation, and that we're going to go for about 2 milliamps. And so what you can do is just calculate if we have a 10 volt supply. So then you just have that V over I equals 4.7. That's just the 10 minus 5.3 over 2 milliamps. Gives you about 2.3 kilo ohms. So this would be the basically, I wouldn't, you want to safely be in the 2 milliamp range. So I wouldn't go too much. Let's see, if this guy goes down, then that means that this guy's going up, right? So I wouldn't make your RZ too much greater than around 2.3 kilo ohms in order to keep the Zener in saturation. We're going to use KVL, Kirchhoff voltage law, to say that basically taking a round trip in a complete loop in a circuit should lead to zero total accumulated voltage if it's a closed circuit. And so what that means for our case is if we go through this way to this point here and this way, we should get the same, those voltages should be equal. So we're going to make a few approximations here. We're going to say that the current through the emitter side of the transistor is approximately equal to the current through the collector, because there is a little bit of current going through the base here, leaking out of the base of the transistor, but it's hundreds of times smaller than the initial collector or the initial emitter current, and so we're going to say they're approximately equal, and that is equal to I load. Now we just need to trace out the route here. So now we use this tidbit to say that the voltage across this resistor is just IL and RE. And then continuing on, we have the drop across the emitter to the base for a PNP is going to be positive. Okay, and that's going to be in saturation about 0.7 volts. And then finally, we need to go back up to the rail through the Zener diode, which is dropping, we're going to call it VZ across it. And that should equal 0. So rearranging, we just have VZ minus 0.7 over RE equals IL. And so simply enough, we have that the current through the load is set by the emitter resistor here and the Zener voltage. And so I guess we'll go ahead and show that if VZ is about 5.3 minus 0.7, we want to set this to about 2 milliamps. So we'll say 2 milli here. It should be about 2.3 K. Okay, one other thing to note is that just like any circuit, there are some limitations, what we call headroom, if you will, of this circuit. So RL has limitations. And in this case, it is going to be an upper bound. And why is that? Because if you think about it, if we have a fixed current here, then if we have a really large resistance, if the device under test is a very large resistance, so if this is fixed and this goes way up, then the voltage also has to go way up across this guy. There are a few conditions for the transistor to stay in saturation. One is that of course, the emitter base voltage has to be greater than or equal to, for most silicon diodes, about 0.7 volts. And the one that I'm talking about in this case of the device under test is actually going to be the emitter collector voltage. Has to also be greater than a certain value. Usually it's low. Maybe we'll say 0.1 to 0.3. So you can just basically write that out by saying that the voltage of this node, aka the Zener voltage, VCC minus the Zener voltage, plus the 0.7 of the VEB, minus the voltage at this node, the collector voltage, or we call it the load voltage, is greater than, say, 0.1. VCC minus VZ plus 0.6. And so this just gives you an idea of the maximum load voltage. And so we could calculate if we're running the circuit at 2 milliamps, then you could do the rest. 5.3 over 2 milliamps, about 2.6. So there you have it. That's basically all the theory that we need to at least understand how to use this circuit. So let's go ahead and build it and check it in reality. Okay, so here it is, all wired up. In this meter we have milliamps. I just have this as the device under test here, so it's you know how these guys test current is just a very small load that they measure a small voltage across. So that's the device under test, and this guy is the voltmeter that we're going to stick around in different places. But this is going to stay put. So let's just take a look here. Right now I have a 10 volt supply from my little handy buck converter, and I'm just going to first probe the diode. I guess this is the base voltage here, is 5.3. And I just looked back at the schematics, and I lied to you at first. The 1N4733 diode, which is what this guy is here, has a 5.1 nominal Zener voltage, which is why I'm a little bit puzzled. But no matter, the diode still should be fully saturated, well over fully saturated, and we're getting, I guess, closer to 4.7 volt drop across it. So that's what we're going to roll with for right now. So what that means is we're actually going to have a slightly smaller current than expected. I also wanted to show you how this is going to track with the supply voltage. So this is our rail. This is our 10-volt supply rail. And just watch how the current changes as I change this guy. So let's say we go up, or we'll characterize it per volt. So let's say it was 1.86 at 10. Now it's 8.8 at 1 volt. And almost 2, or so it's basically about a 2. Well, this is milliamps, so it's about a 0.02 milliamps per volt on the supply rail. That's the drift. That's the drift that we have. You know, this is fine if you're just lighting up LEDs or something non-critical in terms of constant current. But if you're doing, for example, in the following videos, we're going to try to run a constant current through a diode and use it as a temperature sensing device. So if you're doing sensing and this is a critical component of your circuit, then this right here is not going to cut it. So that it will be in the next video. But before we go there, I just want to also check the claim I made about the fact that the device under test resistance matters. So again, remember, if that resistance creeps too high, then it's going to push the collector voltage up towards the emitter, and it's going to remove the transistor from saturation. It's going to take it out of saturation. We're going to start off with the 10 ohm, just to show you that it's working still. And so I'm probing the collector now. So I'm looking at the voltage across the dummy, across the load resistor. So we still got the 1.86 milliamps, and we've got 25 millivolts across that, which this must definitely be a little bit more than 10 ohms, but you get the idea. Okay, now I'm going to move us up to the to a 2.2 kilo ohm, and that should already get us close to, maybe it'll even already get us to the rail. Okay, so we're at 4 volts on the collector, and that is not enough to push this transistor out of saturation, so that's a good thing. And you can see that is confirmed by the fact that we're still at 1.86. But now let's go to, okay, let's just go ahead and double that. So now we're going to have 4.4K. So we should expect exactly double the voltage across that guy, if in fact it's still working. And what do we get? Okay, so see, the current is already starting to sag, 1.36, and we expected double the voltage, so about 8 volts, and we're only getting about 6. So that's showing you that we are already pushing the transistor out of saturation, and our constant current source has been defunked. So that's basically a wrap for this. I just wanted to give a brief introduction to the Zener Diode Enhanced PNP constant current source. And as I was saying, as I showed, the voltage is not going to, the current, the load current is not going to track with the supply that well. I mean, it's pretty good, but for the feature applications I want to use it for, it's not good enough. So in the next video, we're going to show you how to hopefully make this track a little bit better, how to make a little bit more robust current source. Okay, and in the subsequent videos, we're going to show you how to make a how to make a temperature sensing diode, how to turn a diode into a temperature sensor with this constant current source. So we'll see you next time.